All right. I'm going to talk to you about coroutines on ARMS. I've implemented a prototype, and the thing is, it's a demonstration of what you could do if you finish the thing. I mean, it's difficult if you want to optimize it all the way through. So, well, let's start off by introducing myself. So, I'm an electrical engineer by training. Just love C++. Did some Boost stuff. And as he said, I'm an independent contractor, and I'm also open for consulting in case anyone needs someone.
It's also good.
Thanks. All right. My motivation for talking about coroutines, they are awesome. Mainly, no, a more technical reason, you have a low overhead alternative to threads. Not zero overhead, but lesser than a full-blown thread. You do not require an operating system or a scheduler. So that's the main reason. So we're talking bare metal here, wanting to do something in a concurrent way, and their coroutines are quite useful, and they are more readable to state machines. As you can see, I don't mention performance in comparison to state machines, so yeah. Well, there are actually situations, I think, where they can be faster than state machines, but it's not that likely. All right, and they are not well enough known. And by that I mean, well, first of all, who knows what a coroutine is and could use it? All right, a point made. And not only is not everybody familiar with coroutines, but I think there are wrong assumptions on how performant they are and what you can do with them. So that's why I want to go through over that. And so I'm going to give you an introduction to coroutines, which is quite well, we'll see. It's a bit short. And then I go into the implementation, which will include ARM assembly, and we're really going to go down to the into the weeds. And then I go into performance comparison, mainly comparing them to state machines. All right, let's start off with a definition. A coroutine is a function with its own stack. So just like a thread has its own stack, a coroutine has such, that can interrupt its own execution and be resumed later. So a thread is interrupted from another source, mainly the thread scheduler. The coroutine says itself, I'm done, do something else, and then somebody else has to tell the coroutine to continue. Right, let's visualize that. So that's a normal subroutine. As well, we call it function in C++. So you call the thing here, then it does some work and more work, and then it's done and you're back in the main. Should be quite obvious. And a coroutine might look like that. So that's rather fictional code, but similar to what my library looks like. You declare an object of a coroutine, you spawn it, at which point it enters here, does some work and yields. And the yield will cause the coroutine to interrupt itself. That is, it jumps back into the main context, and main does something else. At some point decides the coroutine should do some more work, re-enters. At that point we return from the yield and do more work in the coroutine. I hope that makes sense. That's the basic idea. I thought long and hard about finding an introductory example, and there are good examples, but I would need to explain them for 10 or 20 minutes, so it would be a problem. I hope you can think of some application where you have to, pause in between steps in your application, or something where you would use threads or that sort of thing, or maybe you have a timer occurring frequently and it needs to do something. Some application like that. I hope that's simple enough. All right. So the first thing we can do is some form of concurrency, which could look like that. So for simplicity's sake, I have the same coroutine function, which has one interruption point, and I just spawn two of those. So I first create coroutine 1 and 2, then I spawn the first one and the second one. So when the first one is spawned, it does some work. Once it's done, I spawn the second one, then that does some work, and then I re-enter the first one and the second one. So I have my fiber of the first coroutine here, and interrupt it here, and I have the second one here with one interruption while it re-enters the first one. Now, I wish to point out that this is not real concurrency. So there are not two things happening at the same time. I'm sequencing, basically, slices of my coroutine function out. That is, in a thread, if you're multi-threaded on a multi-core processor, you have things really happening at the same time. Here I don't know exactly what's going on, because I control when I re-enter the coroutine and when I leave it, which means it's completely deterministic, and I don't have race conditions. But it's from a conceptual point of view, it's sort of concurrent. Because from the way the coroutine sees it, it's happening at the same time, if you will. All right, now, since that is the case, since the yield is deterministic and at particular points in time, we can use it to pass values out from the coroutine. Because well, we don't have race conditions and nothing, so what we do is we yield A1, A2, and A4. Also then the yield keyword actually makes sense, right? So when we spawn, we enter the coroutine, go into line 3, into the yield, and return from spawn with the 1. Once we re-enter, we start in line 3, go into line 4, yield the 2, and get the 2 back in line 13, and we do that one last time. At this point it returns, we get the return value back in line 14, and then we know the coroutine is done, because we return from the implementation function. All right. Okay, unless somebody asks, I'll assume it makes sense. Now, what we can also do is we can put a value in on re-enter or spawn, and can use it in a more elaborate way, because at this point we're shifting bits up basically. So returning the lowest bit, the second lowest, and the third lowest, and that can be expressed in a loop like that. So what happens is we spawn the coroutine, it initializes the value on the stack with A1, we yield the value, and as long as yield returns a true, we continue in the loop, shift the value 1 up, and yield it again. So we spawn it with true, that actually gets ignored here. But once we re-enter, we set it to true. It yields, returns a true. We go to the loop, yield the 2, and then we call it again with a true. We have a 2 in the value, it gets shifted 1 up and yielded, and we're on a 4. And in line 16, we put in a false. At this point, the loop breaks, and we return a 0. Now, a few things I would like you to notice. We use the stack, which is, again, it's the point of the coroutine. We have it has its own stack, but it's quite useful because it's very natural to use the stack instead of putting it as a member somewhere. And we are putting the yield, so the interruption, into a loop condition, which is quite a simple case, but it's quite powerful if you think about it. You can nest it anywhere, basically, and interrupt your coroutine at any point. It's not possible with the state machine. Also, it's quite a readable function. Okay, so let's summarize the properties of coroutines. They are deterministic. That is no real concurrency in a strict sense. We can pass values out on yield and in on re-enter. So we can communicate between the coroutine and the main context. And the third point is obvious if you think about what a stack is. We cannot move the thing in memory, because we might have references to its stack. So once you move the thing, the references are invalid and you're pointing somewhere, and you cannot know when the compiler generates code that references the stack. So the thing can't be moved, but we're in a bare metal environment here, so we can control in which memory areas we're storing things. So we can actually store the coroutine as a state. So we can save the thing in flash memory, restart the controller, restore the coroutine if we have the stack in the same place, and continue from there. Also useful for deep sleep and whatever you want to do. And the only constraint you have is the stack size, which is different if you're, for example, multi-threaded and you're using a library that's not thread aware. You might run in all sorts of problems. You don't have the problem with coroutines. The only thing you can get is a stack overflow. And so you can use any other library like the STL or whatever you want to do in the coroutine, as long as it's well, as the stack suffices, and you can set the stack by hand. So that should work. And the sixth one is I can use the yield expression, or better yet, the re-enter, as a callback alternative, actually. I have not implemented that, but Boost ACO has, where you can start an async operation, and normally you pass in a callback. But if you use Boost coroutine, you pass in a handle to the coroutine, and the coroutine yields and waits until the async operation is complete and then re-enters. So it's a very nice way of modeling asynchronous operations. And of course, you can see the same thing on a controller, starting something on the hardware and say, well, re-enter when it's done. So again, that would need to be done. All right, that's a basic information about the coroutine. I would give you a few minutes if anybody's confused, because if you don't understand what the coroutine is, the rest of the talk will make sense to you. So should I clarify something? Yes.
Can you use the compiler output to get the exact stack size?
The question was, can you use the compiler output to get the complete stack size? You set it by hand for the coroutine. You pass in a buffer to say, that's my stack I want you to use.
But the compiler already knows how much stack it's using. It's going to use, right?
Yes, the compiler knows that. Well, actually not. If you use function pointers, it doesn't.
Okay. Yeah, okay.
That would be a question for tooling.
Yeah.
All right, then let's jump into the assembly. First of all, we need to define how it should look. It is a bit complicated, and I hope it makes sense. We have two contexts. And by context, it's mainly the stack, but also a bunch of registers which tell the processor what it should do, actually. And that's what we call a context. And what we need to do is we need to jump between those. So I tried to visualize that. The red lines are the context jumps. So we call spawn, and that calls something make context, which is assembly. It looks like a function. It isn't one, but it's linked like one. And from the point of view of the main context, we'll start in line 4 called spawn, and spawn returns in line 8. That's, I hope, makes sense. And we call re-enter, and it returns in line 12, and in between it executes whatever's on this side. So we call spawn, that executes make context, enters the coroutine. The coroutine calls yield. We jump out of the coroutine context, are back in the main context doing something here, and the next thing happens to be the re-enter. Which point we call re-enter, that calls the switch context, jumps back into the coroutine, and at this point we return from the yield from the point of view of the coroutine and return, and are back in the main. So we model it like a function call, and it's a bit confusing because you're calling the make context here, but then it returns somewhere else. That's, yeah. Or as UML, so you call spawn instead of returning here, you go into the coroutine, call yield, and yield doesn't return to the coroutine but returns to the main. I call re-enter, and it doesn't return to main but returns to the coroutine, and then the coroutine returns finally. So that's the jump, and we have some magic going on there in assembly. All right, already mentioned the context. Now we've got to define what that actually is. And those are a bunch of registers. So the first one of those is the stack pointer, which points to the lowest element on the stack, just to be correct here, because ARM has a descending stack. So it's start at the highest address and move downwards. And the thing is normally decremented on function entry and incremented on exit, because the compiler just says, well, I know how much stack the function will take, so I do it once. And in a simple GCC generated example, it looks like that. So now in addition, we have the frame pointer, which is a GCC convention. It's not in the ARM standard as far as I know. And that points to the address once we enter the function. And then we have the stack pointer to the lowest address, so that's the frame of the stack the current function uses. So what this does is it sets the frame pointer. It stores the old frame pointer, it sets it to the current location, and sets the stack pointer to the same location because we don't use any stack. We do a no operation, reset the stack pointer, load the old frame pointer back, and return. So that's simple enough. The return works through the link register, and the link register stores the return value. Again, we need to take account of that. That points to the code location of the function call. To be precise, one further than that. So when I call a function, the next address in the program code is what is stored in the link register. Returning means just jumping to the location. We push the link register onto the stack for a new function call, which is obvious if you have nested function calls and you already have a link register set. And that's how it looks. We push the frame pointer and the link register onto the stack. We set a new frame pointer, call bar, and BL is a branch command that stores the old link register value. No, it doesn't store. It stores the return value in the link register. So that would be this line. That is stored in the link register. It calls it, bar calls bxlr, jumps back to this location, and we continue. And then we have the stack pointer reset and pop back the old values and return. Okay. Now, more important also, or not more, but also important are the argument registers. Because if we need to implement a function, we have support from the architecture, if you will. We have 4 registers that store the argument values, which are A1 and A4. They also store the return value. And large values that exceed the 4 registers are stored as a reference. A1 stores the return value, and they are only valid in the local context. I hope that's the correct term. That is, if you call a subroutine, the subroutine might change the argument registers as much as it wants. We don't need to care about that. So if our function changes them, yeah, it might just as well do so. And IP is an additional scratch register. That's the intra-procedural scratch register. I don't know where it's used. Well, it's there for the compiler to utilize while calling subroutines. That's how it looks, this time with an optimizer. We have the value of x in A1. We have the value of y in A2. And we return the added value, so it's stored in A1, which holds the return type, and then we return. That's simple as it gets. And then we have the variable registers. Now, ARM is a Loadstore architecture. That is, if I want to do something, I can't just say use this value from memory and this value from memory and add them or something, but I have to load them into the register. So I point to memory, load the value into register, then do something. And I could use the scratch registers. In addition, I have the 8 variable registers to do so. And they are, that's that point. They are persistent. That is, if I change them, I need to store the old value and restore it once my function leaves. So I can't randomly just write stuff in there. And normally the old values get pushed on the stack. And that's how it looks. I had to force the compiler to use the variable registers and not the argument registers. So that's why we have 4 arguments here. And it still uses the link register for 1. So what it does is it pushes the 3 variable registers plus the link register onto the stack. It loads wherever a 2 to a 4 point. Now the square brackets mean it's a pointer, and load where it points at. And then it adds the 3 values, stores the result in our other scratch register, and stores this value where A1 points, calls bar. Now, it doesn't need to modify the arguments for bar because they're already in the right position. I'm just forwarding them. So that's why A1 to A4 are untouched. And then it pops back the old values and returns. To summarize, we have the argument registers. Now, since we model our context switch as a function call, we can just ignore them. We use them, but we don't need to take them into account as a part of the context. We do need to do that with the variable registers, because we need to keep them at the same place when we jump from one context to the other. The frame pointer I mentioned is R11, that's V8. So we just take that, use that in the same way as the variable registers. We have the IP, the other scratch register, and we can just treat that like every argument register, basically ignoring it because we have a function call, so compiler has to assume it changes. Then we have the stack pointer in R13. Now we need to swap that if we want to change the context. And we have the link register in R14. Which stores our return location, and in R15 we have the program counter, which is the current location of the code to be executed, but we're not touching that directly. We're using branch commands. All right, so that's the context we have. Now, I'm quite certain if you had an operating system, you need to do more stuff, but we're bare metal, so why not? So, to one last C++ slide before more assembly. When we want to spawn a coroutine? Well, we have the spawn function here. It was quite important for me to allow the usage of function objects. So you could put in lambdas and not only C functions. So the way we do that is we call this make context thing. That's the assembly, which gets at this pointer a function pointer, no, not a function pointer, a pointer to the function object, and a pointer to the executor function. Now that thing constructs our new context and then calls the executor and passes in a this pointer and the function object. And so when we are on line 11, we're already in the context of the new stack of the coroutine. So the first thing we do is put a function object onto the stack. And then we called it. That's basically the whole trick. And then you can have anything in here, really. Now, the function might yield as often as it wants, but once we return, we know we're done with whatever our implementation is. So we store the return value, say we're done, and switch out of the context for one last time for the coroutine. Now, I don't know if anybody notices, but there's a scope lacking around the function object, but that's not as important. Now, what I would like you to notice is that the stack pointer, when we get to spawn, the stack pointer already points to a valid section of stack. The constructor for the coroutine just gets 2 pointers, so you can use it without any allocations. And the stack pointer is the first element of the coroutine, which is important because if I then point to the coroutine, I always point to the stack pointer, which makes the assembly easier. And that's what it looks like. So that's how it's linked for C. Now it's make context 0 because it gets 0 arguments. There are 1 and 2 in addition. If you want to pass in values, I'm ignoring those for make context and show them to you for switch context. So what we do is we store the variable registers in the link register. And then we swap the stack pointer. That is, we move the old one to V1. We load the new one from A1, and that's why it's important the stack pointer in the coroutine class is the first element, because that points to the coroutine and we just load whatever's there, and thus save time dereferencing and that sort of nonsense, and just know it's the right location, and you have to assert that through some trickery. And then we store the old stack pointer in A1. So at this point we're in a new context already, and we just call the function and start our coroutine. Now we don't need to touch the argument registers because they're in place. So you have A1 here, and you have A2 here and here. So we just pass them through. A3 is ignored by A3 by the executor, so it works. Rather short, actually. All right. Now once we have that done, we're in the coroutine. Now we need to switch between coroutines. And I'm lazy, so I wrote void star instead of coroutine there. So that's what you basically get. We start off with a switch context 0. That means you have a coroutine that doesn't return a value, so it doesn't yield a value and doesn't get one. And that's what the assembly looks like. So we have this switch context 0. The first argument is the stack pointer. The pointer to the stack pointer. So what we do is we store the old context with same push command. We swap the stack pointer. And then we restore the old context. Now that's again popping the link register there. And the whole thing takes 8 cycles to push, because when you push something, the link register doesn't count. Well, in thumb code anyway. So that's 8 cycles. That's 1, 2, 2 again, 8, and we have overall 22 cycles to switch between context. That's really the bare minimum I could think of. I mean, if anybody finds something we can reduce the amount there, I'd be happy to know it. Okay. We might now want to pass in values. And the question is, how does it look? Now, because it's basically the same idea, I put it into one coroutine. That's a coroutine that yields a 32-bit value and gets a 64-bit. Everything beyond that is prohibited, and you would have to pass a reference through. So what you have is a yield that takes a 32-bit value and returns a 64-bit, and the other way around in re-enter, of course. You put in the 64-bit and get the 32-bit, and we put the argument as the first one. So, how does the switch context 1 look? Well, actually, quite similar. we just moved the stack pointer location to A2 from A1. And the reason this works is the following. We're calling yield, or well, switch context in yield, and that's a function with this signature, returning a 64-bit and becoming a 32-bit. But once we're here, we switch the context. We're back in the main context, where we are, in effect, in reenter, which is a function that returns a 32-bit return value. So that's a strange thing that we call it here and return from another function. At this point, the 32-bit value is already in register A1, which is where we expect the return value to be. So we just return. We don't have any overhead for passing a value through. So that's, well, I think that's quite nice. And the same holds true for switch context 2. So you just pass the A3 one further. You have the 64-bit value in A1 to A2. And once you're down here, you've switched the context. You're returning now from, in effect, the yield function that expects a 64-bit value, which is already in A1 to A2. And so you have, for passing through 32-bit and 64-bit values, you have 22 cycles you need. All right. Everybody confused? Obviously. Okay. Well, that's basically the implementation. It took a while to come up with that. Seriously, I mean, any questions thus far? Or
Does it support suspending from within a nested function call?
yeah, sure. Because everything you have there is just on a stack on a variable register, so you can nest the thing as deep as you want.
So this would be different than the Coroutines proposal that doesn't have a stack component. Coroutines are the proposed standard.
In the Coroutines TS, yeah, I think I've tried to get that one. It's more integration into the SCD future and how to model that as a coroutine. So yeah, I think that's completely different. That's really the basic of having a function which you can yield from and yeah.
If you're deep on your call stack and you yield, when you return exactly the same point you did before, even if you're several functions call deep.
So the question was, if you deepen your call stack and you yield, do you return to the same location? Yes. That's exactly the same. Right. Still costs the 22 cycles. Yeah. So you can nest the thing into a lambda you put into an STL algorithm that you put into a ranged for loop, and it still would work, yeah. Or something like that. Or whatever you want. You just need to pass the handle to the yield object through. That's all you need to do. Yeah.
Your assembler, but it doesn't understand what you're doing in assembler.
Right, so the question is, can't the compiler optimize in a destructive manner, if you will, to reorder things? Yeah, that's the reason I did it that way, that you have a separate assembly file, where you just have hard-coded the symbols in, and then you link against those, so the compiler has no clue what's going on, because you really you don't have any line assembly.
So with compiler support, you could probably expect a better code gen than...
You could maybe expect better code gen if you get around the fact that the compiler will probably operate a lot of stuff you need away. Because it might not know what's going on. Assume you have a normal function. Oh yeah, that. Well, but then again, what would you actually want to optimize? I mean, the thing is, you don't get around swapping the stack pointer, and then you need to store the variable registers, which is the majority of the time you have. Those are the 16 cycles you need. So the only way to optimize that is if the compiler knows what's going on in the variable registers, which you then again can't know because you can use in some sub-function which could be hidden behind a function pointer.
But it can know in, like if I create a coroutine and then re-enter twice,
Right, and it could.
then it could theoretically just inline what, that piece of the code right at the re-entry site.
Right, if the compiler sees the whole code until you yield, yeah, it could optimize.
If between, then it all breaks down. But
Right. But actually a question also, could you maybe do something with inline assembly already? But that's, I'm not sure. Okay, so the statement was I could inline the assembly. Well, the problem then in addition is I would need to know where my arguments are, which is what I can control there as well, because it has C linkage. So I wouldn't know. but I mean that's probably solvable. That's just not something I did. And then I would just worry about the reordering part. But and then it's just 2 cycles. I mean, you just have the call and the return you save. I think.
Kennen Sie eigentlich das Bochumer Institut für Technologie? Nein? Dann heißt es jetzt Ohrenspitzen. Denn wir machen Ihre Ideen zum Erfolg. Wie? Wir stellen Ihnen geeignete Forschungspartner aus Hochschulen und Universitäten zur Seite. Projektpläne, Förderprogramme, Antragstellung, auch das übernehmen wir. Lassen Sie sich diese Chance nicht entgehen und starten Sie mit uns durch.
All right. Now we're going to look at a few simple state machines, and I was in the state machine talk yesterday, so that's way more awesome than what I have. I just had the simplest one just to show the basic idea of it, and the thing is, I mean, 100 lines of code on a slide to demonstrate it's superior is not really efficient. So that's a brutally simple state machine. It just has state 0 where it calls f, state 1 where it calls g, and state 2 where it calls h. So we call it thrice, and then last time it sets the done bit. So simple enough. And that's what it would look like as a coroutine. And by the way, that would work. I mean, I have the library there. That's real code. Of course, you need to construct the coroutine object there, but you just write yield f, yield g, and return h, which I find, well, already more readable. Now, how does the performance look? And I just generated the code with GCC. It loads the state, pushes the old values, compares against 0, and then jumps to the state and works with it, which is then setting the new state and storing it, and calling the function and popping back from the stack and returning. So that's 11 cycles. Now that increases if the compiler doesn't optimize it in any other way. It increases per state. So if you compare it to 1, you have 1 more cycle, and the things are 12 for G and 13 for calling H, which is still not that much because that's how it looks on a coroutine. Now the 14 is not really correct because we would also need to copy the function object and that sort of stuff, and I don't know how long that takes. So that's not in there. So it's probably more than that. But then you get the 14 for creating the context, plus the 4 for preparing the call of f, plus the call of the switch context and the 22 cycles of the switch context, which would be 41, plus a bunch more. And then if we re-enter, we have the 22 for the re-entry, 1 for calling g, 1 for storing the return value in v1, I think. No. Oh no, it stores the stack pointer. That's what it does. It calls switch context again, and those are 47. So you have as soon as you created the context here, you have a consistent, always the same amount. Now 47 is a bunch more than 11 cycles, which would mean if you have around 70 states, the coroutine would get faster. Which, if you have 70 states, I don't know, state machine is the right choice anyway. Yeah, so that's the performance comparison. Now, of course, you might think, well, 11 or 47, I mean, that's fourfold. But then again, I think 35 states are not that much to begin with. So in absolute terms, I think it's quite performant. All right, now here's a more contrived example. I have a state machine which does something, and it has one branch. And now you might ask, why would you use Ychar? Well, I've written a systems library using the Win API, where you have to use Ychar, and I'm scarred for life. So that's the reason there. You just have one alternative. So in the first state, it asks, do I have to use the Ychar or the normal char? And returns, goes into state 1. Then either uses the Ychar and reads from the buffer and later on handles it in the next state, or it switches to state 3, reads the buffer and then handles in state 3. Now, I don't want to make it out that you need more memory, because you could put those two things in the same memory region. But what I would like to point out is that I had to explain the example. It's not as easily readable, and as a coroutine, it looks like that. So you have you put it on the stack, get the toggle bit for the Ychar, you yield, and then you either call this block or this block and have one yield in between. So it actually looks like a normal function. You just have this magic yield keyword, which then interrupts its execution. And you can nest it. So because I'm lazy, I don't want to write the whole function twice, so I'm creating a template, because if you can use a template, you should use a template. Put the buffer on the stack, yield here, I just have to need to pass on the yield object there, and it works. And of course, that's a contrived and simple example. You could, as Simon asked, pass it in as deep as you want. Okay, and I'm done way faster than I expected. So, well, at least there's room for discussion, I think. So, so you can check out the library at GitHub, which I tested it as on an STM F4. You can write me if you have any questions or want to develop on the stuff, or need some help developing something. Obviously, I'm fast. Right.